Hello, students. Hello, welcome back. Now that we've learned about exo and endothermic, we're going to talk about phase changes and whether they are exo or endothermic. So, first of all, let's talk about endothermic. This is where heat needs to go into the process or the physical change. So, heat is needed to break intermolecular forces, to overcome the intermolecular forces. So, heat has to go into it. This is what happens for melting, boiling, and subliming. So, melting again is solid to liquid, boiling is liquid to gas, subliming is solid straight to gas. So, in order for something to go from solid to liquid, let's think about this. We have the solid state where the atoms are very close vibrating, and then we're going to pull them apart so that the molecules or atoms can flow around each other in a liquid. To pull them apart that little bit means we need to put energy into it. It can't happen on its own. We got to put energy into it to release that solid forces, the intermolecular forces in the solid, so that they can flow around each other. Same thing for boiling. We have a liquid where the atoms and molecules are touching each other and flowing around, and then we're going to pull them apart to the gas state. Okay, we got to put energy into that to do that, to pull them apart. Okay, so I mean, this makes sense, right? When you boil something, you heat it up, you add energy into it, right? You have to heat it up. So that's how you boil something. So that makes sense. All right, now exothermic. This is the opposite, and this one's a little harder to understand. Exothermic, heat exits out. Heat is released when intermolecular forces form. So this is freezing, condensing, and depositing. Freezing, of course, is liquid to solid. Condensing is gas to liquid, and depositing is gas to solid. So when these things happen, intermolecular forces are forming. We're going from liquid, where they're flowing around, and then we're going to solidify it into the solid state. So we formed intermolecular forces there to keep the solid close and tight together. So that lowered the energy. So the heat has to go somewhere, so it exits. Think of the gas, lots of energy. The molecules are going all over the place, and then we're going to pull them together to make a liquid. Okay, that's less energy. Okay, so where did the energy go, right? It had to exit and go to the surroundings. Exothermic, heat exits when we freeze, condense, or deposit. Okay, great. Moving on. Specific heat capacity. Specific heat capacity measures how many joules it takes per gram or degree Celsius to heat something up. So specific heat capacities are constants. They can be measured, and they're different for all different substances. So you can find these values in a reference table, specific heat capacity. Again, the joules it takes to raise to raise 1 gram of that substance by 1 degree. So liquid water is different from ice, which is different from water vapor or steam. And then we have some metals, magnesium, mercury, iron. We have another liquid, ethylene glycol, and ammonia in this chart. So specific heat is a constant, and it's how much energy it takes in joules to raise that substance 1 gram by 1 degree. So we can calculate specific heat. So let's look at an example. Scientists determined 67 joules of heat are required to raise the temperature of 13.18 grams of magnesium by 5.0 degrees Celsius. We're going to calculate the specific heat capacity for magnesium and see if we get what is in the table here. So again, it's the joules over grams times the change in temperature. Now, the equation we're using is actually Q equals ms delta T. Let's look at that. Q is the symbol for heat. M stands for mass in grams. Capital S is the specific heat capacity. And delta T, that triangle is delta, and it's the change in temperature in degrees Celsius. One more time. Q is heat in joules or kilojoules. M is mass in grams. Capital S is specific heat capacity. Delta T is the change in heat in degrees Celsius. So we're solving for specific heat capacity. So we're solving for S. So that's going to make S equal to Q over M delta T, right? And just follow the units. Specific heat units are joules over grams degrees Celsius. So we're going to plug in our joules over the grams degrees Celsius. So joules, we have 67 joules, so that's on top. Grams, we have 13.18 grams of magnesium. And the temperature changed 5 degrees because it was raised by 5 degrees. So that's a positive 5.0 degrees Celsius. So we just plug those in and we'll solve for S, specific heat capacity. So we have joules over grams degrees Celsius. So 67 divided by 13.18 divided by 5.0 equals 1.01669 joules per gram degree Celsius. Sig figs are important. Which has the least sig figs? Well, 5.0 is 2 sig figs and 67 is 2 sig figs. So we are limited to 2 sig figs. So 1.0 joules per gram degree Celsius is our answer. So that is how you calculate a specific heat value for a substance. Again, we rearrange Q equals ms delta T, which is a very important equation. We're going to use it more in the next video. See you in a minute, GCC. Bye-bye.